Hello students, we are going to triangulate some polygons. And what do I mean by that? Well, we're going to create a polygon by making a circle and taking some points. Let's do 7 points this time, but some collection of points. And we're going to connect the ones that are next to each other on the circle. And then we can get rid of the circle altogether. We don't need the circle. We don't care about that. We just wanted to make sure that we don't create a situation that's like something like this, where we can't draw an edge between any two vertices without crossing a line. Here, I can draw edges between any of those vertices without crossing through a line. So, okay, what do I want to do? I want to triangulate this polygon. So I want to turn it into triangles. So basically, I'm going to be connecting vertices with edges. Let's do that, and maybe that. And now you can see every piece is a triangle. Okay. So what I want to know is let's let Cn be the number of ways to triangulate an n+2 gon. Now you might say, okay, why the n+2 gon? Well, let's let the first case be the triangle. That makes a lot of sense, right? Let the triangle be the first case, so I don't have to draw a circle to get a triangle, but whatever. I have a triangle. I want this to be the first case. It's already triangulated. Boom, 1. So it makes sense to do this if you think I'd like that to be case number 1. And then for case number 2, well, I don't really need to draw the circle in order to get a good square, but actually that's not such a good square, but it's fine. They don't have to be evenly spaced. The problem is the same regardless. So what could I do with the square? Well, I could split this in 2 ways. I could either do this or this. So there's 2 ways to decompose this into triangles. So I'm going to get C2 for the foregon, because I have the n+2, equals 2 for the number of ways. Okay. Now, what about C0? Could I go to C0? This would be like collapsing on itself, like a degenerate triangle. So I'm going to allow C0 to be 1. The number of ways, we could just leave it alone. Okay. That said, let's move on to C5. And so you don't have to sit here and watch me draw a whole bunch of pentagons. Let's go to here. Okay. So how do I find C5? Well, there's one thing I could do is I could label a vertex. And I could say, okay, what am I going to do? I'm going to look at where this vertex connects. For example, the vertex could connect here, or it could connect here, or it could connect nowhere. And you'll note that in each of these cases, I still have a foregon to fill in. Well, I'm going to repeat that. I'm going to repeat each of these, so I'm going to draw them each twice. Why do I want to draw them twice? Well, because a foregon has 2 ways of filling it in. So if I draw this line, I still have a foregon. That could be filled in 2 ways, this way or this way. And if I draw this one first, I still have a foregon over here. That could be filled in 2 ways, this way or this way. And if I draw this line first, I still have a foregon. That can be filled in 2 ways, this way or this way. But does anyone see anything wrong with this? What about these 2? See, it doesn't matter which line I draw first. I can draw this line first and then this, or this line first and then this. When I do this kind of computation, I'm taking into account the order that I'm placing the lines, and I don't want to do that. So what I'd have to do is I'd have to get rid of one. And then I'm hoping maybe that C3 is 5. Maybe. I need a better way. So what I could do is, instead of distinguishing a vertex, I could distinguish an edge. And that edge must connect somewhere because it's part of a triangle. These two vertices are part of some triangle somewhere. So I could do that, I could do that, or I could do that. So I'll shade in the triangles I get. But I must be in one of these cases because that edge must be part of a triangle if I've triangulated my polygon. So let's write out what these are. Well, this has a triangle on both sides, so I could think about that as a C1 times C1. This has a square, or sorry, not a square, definitely not a square, but it has a C2 because that's a fourgon. And I could write that as C2 plus C0. And over here, I have a fourgon on the left. Okay, that's good. Seems to work. But we're going to take this up. And let's see what this is. Let's actually do the computation. Well, this is 1 times 2 plus 1 times 1 plus 2 times 1 equals 5. So I get that C3 does, in fact, equal 5. But now let's go for C4. And that is for the 6gon. So I'm going to distinguish a base. And it must connect somewhere. And I'll shade in these little triangles that we get. 1, 1, and 1, and 1. Okay. So now what do I have? Well, if I look at the choices, I have to deal with the choice on the left and the choice on the right. Here I have C0 on the left and C3. Here I have C1 and C2, C2 and C1, and C3 and C0. So what's this going to be? Well, I can see this is going to be 1 times 5, 1 times 2, 2 times 1, and 5 times 1, which is 14. So I get C4 equals 14. Okay, so now let's try to think about this in general. So suppose I wanted to find, say, Cn plus 1. Well, notice that C4, the first possible case, if I connect my distinguished edge to the very next vertex, is going to give me what? Well, it's going to give me a polygon with one less. So what am I going to get? Well, I'm going to get a C0, Cn, plus C1, Cn minus 1, all the way to Cn minus 1, C1, and I'll end with a Cn, C0. And I finally get the number of ways that I can triangulate an n plus 2gon to be the sum from k equals 0 to n of ck Cn minus k. And that's my answer that works for general n.